Thank you very much for the introduction. So I want to talk about the quantification of the Reynolds stress tensor using Phloem RF. Phloem RF is a technique I presented last year, and actually this research is directly motivated by discussions I had on last year's meeting. So Phloem RF is a technique where we employ the magnetic resonance fingerprinting framework to simultaneously quantify relaxation times and velocities using both a variable flip angle and variable velocity encoding moments to encode both sets of parameters. Now, in this work, I want to limit the variation of the flip angle and just use a constant flip angle. Why this is done, I'll explain a little bit later. The whole quantification is based on an undersampled time series. In this work, we used 5 projections. There should be an animation here. Maybe it comes in a second. No, it doesn't. There's a GIF which usually shows you an undersampled time series. But this time series, each pixel, the signal evolution over time tells you what the velocity and relaxation times is. But in this work, I'll only focus on the velocity quantification. Here, okay, this plays very quickly. The velocity is now not encoded by finite velocity differences we usually compute in phase contrast MRI, but rather it is based on the observation of the phase pattern that we encode based on the knowledge of this velocity encoding pattern that we vary pseudo-randomly over time. And what the advantage of this is that we now don't rely on finite phase differences, thus the 2 pi periodicity of the phase is no longer a problem because this phase pattern is unique even for very high velocities compared to our encoding velocity. Here we use 60 milliteslas per meter times millisecond squared, which equals a 20 centimeter bank, but we're well able to resolve velocities of 2 meters per second. So this is a unique feature of Phloem RF, which might be useful to the quantification of the Reynolds stress tensor. And the Reynolds stress tensor is a fluid dynamic tensor, which tells us something about this distribution of velocities within a single voxel. And it occurs all the time in fluid dynamics and can potentially tell you something about turbulence or pressure change, for example. Here, if we look at this stenotic measurement, we can see after the stenosis, there's a velocity jet, and we have the shading of the magnetization next to the jet, which is linked to broadening of the velocity distribution, here in this case assumed Gaussian. And this is really not an information which is contained in the velocity map, because the velocity map only gives us the mean, the mean velocity of this distribution, and the standard deviation is not encoded. But if we assume that these distributions are Gaussian, well, the signal decay we observe as a function of the velocity encoding moment is simply the Fourier transform, thus also a Gaussian. And Tarasen et al. Showed us that we can linearize this problem, assuming Gaussian distributions, and simply by solving this linear set of equations, we can determine this tensor, which in 3D is a 3-dimensional tensor, and it's symmetric, so we have 6 independent variables we need to quantify. And we did exactly this using the Phloem RF approach. Now, what's the advantage of Phloem RF? Well, the advantage is that we have this undersampled time series of data points, meaning that we have much more data points to fit to. Usually, the method by Harrison et al. Uses 7 data points, which is the minimum required number to solve this set of equations. But we have much more data points in the order of 50 per cardiac phase. And because we quantify velocities based on this phase pattern, we can use much higher encoding moments while still maintaining the quantification of the velocity. And this allows us potentially a better sampling of this decay curve and allows us to sample much further out, potentially being more sensitive to regions where we have low stresses. But the disadvantage is, due to the undersampling, we have a significantly decreased SNR in each individual time point compared to the reference method. So I want to show you the preliminary results. I performed this stenotic measurement. You can see the velocity jet, but already here you can see that in some pixels the velocity quantification failed, and this might be because I pushed the velocity encoding moments too far, meaning that we dephased too much of our magnetization, and robust quantification of the velocities was no longer possible. And you can actually see in the Reynolds stress tensor, which now gives you a a measure of how strongly magnetization dephases, you can see these correspond really to the regions where we have highest stresses, meaning the broadest distribution of velocities. And now this tensor gives you some information. It's hard to say what it really means. Potentially you can see some turbulence, potentially you see pressure changes. But in any case, it corresponds well to the reference measurement. Although the peak stresses here are about 15% lower with Phloem RF than the reference measurement. But a direct comparison between these two is not really fair because this is 3D measurement and has isotropic resolution. Phloem RF is 2D, has fairly large slices, and the measurement times are vastly different. But it's just to show you that, in principle, we can quantify the Reynolds stress tensor, and there's potentially some gain to be had using this different way of encoding velocities. But there's one problem. We can't quantify relaxation times and the Reynolds stress tensor at the same time, because those are both quantities which depend on the magnitude variation of the magnetization, and we eliminated it by fixing the flip angle, because if we were to use a variable flip angle, the problem is the signal in flowing regions is really hard to describe on a quantitative level. Just if we look at the signal change as a function of the heart rate, then you can see that this signal is fairly difficult to describe, and there are lots of other parameters which also play into this. And so if we don't know the baseline, then it's really hard to know what the additional dephasing of the Reynolds stress tensor is. So to conclude, in my opinion, there's always potential gain to be had once we deal with multi-parametric mapping, and here we investigated the use of fingerprinting with the quantification of the three-dimensional velocity vector and the Reynolds stress tensor, so the complete set of 9 parameters. It's potentially an alternative method to quantify the Reynolds stress tensor. But these high encoding moments that we can apply with Phloem RF, they also come potentially with a drawback because they make us more susceptible to non-normal distributions of velocity fields within a single voxel. So we're more susceptible to skewness or even higher moments. And we're not really exploiting the fact that we have all these observation points over a large range because we're still solving this linear model, and more sophisticated reconstructions could potentially also exploit that. We have susceptibility to higher moments of the distribution. And with this, I'd like to thank you for your attention.